So I'm going to record. So what we're going to be doing in this session, is covering a couple of things just to wrap up the learning module 2 that has to do with capacitance. So the first is just kind of wrap up. I don't know why it's having. So just to wrap up the capacitance learning module, we're going to talk a little bit about dielectric constants and permittivity. We already did this. We already talked about this, but just we're going to wrap up that topic because I think it's important for your lab practice. And I want to do one more exercise that's similar to the ones in the homework test. So you have that one recorded, and we'll wrap up. That would wrap up learning module number 2. Okay, so let's wrap this up with regards to capacitance constants or dielectric constants and permittivity. Remember that we talked about permittivity. I need to correct this slide, by the way, because permittivity, we had said that it's with 2 T's, remember? So it's permittivity. I need to correct these slides. Permittivity. We talked about permittivity, and basically a very general, broad definition of permittivity. It's this constant value or property of a material that has to do with its capacity to allow the storage of charge. So that's why it's called permittivity. So like permit, like allow. So remember when you think about permittivity, it's like allow, permit. And so permittivity is something very important with capacitance because remember that there are 3 things that affect capacitance value. Remember what are those 3 things for a physical dielectric material?
To allow
The distance between the plaques or whatever we're talking about and the superficial area. And so the permittivity is going to be one of the factors that's going to affect capacitance. And actually the permittivity of the material is we're going to be referencing, or we've already been referencing it. And that permittivity is usually related to a material that we call a dielectric, or a dielectric material. That is this material that's the part in the middle of the sandwich of the capacitors. Whatever we put in the middle, called a dielectric material. And the dielectric material is associated to a certain permittivity. So sometimes the term permittivity and dielectric constant or dielectric are used interchangeably. So we may be talking about permittivity or we may be talking about dielectric constant. We're really talking about the same thing, but with a different name. There are terms that are synonyms or equivalent. So a dielectric material is going to be able to store electrostatic energy. By the way, when we're talking about charges and permittivity and dielectrics, remember that we're still, and up to until further notice, we're still talking about charges that aren't moving. Okay, we're in a static situation. Next unit is where we're going to start moving charges, and that has to do with electrical circuits. But right now, charges aren't moving. And that is electrostatic energy. And so in a capacitor, we've got 2 plates that are conductors, and there's something in the middle of that sandwich. That thing in the middle is an insulating material, meaning it's a material that doesn't conduct, or else it wouldn't make sense. It's a material that does not conduct electricity. It's an insulating material, and that material is going to have a certain permittivity, and it's going to have a certain dielectric constant. And so, remembering the structure of the capacitor, we've got the 2 plates that are conducting. We've got this here says connection lead. The lead is only whatever we're connecting to the plates, And the dielectric material or the insulating material is what is in the middle. And so if we're talking about permittivity and dielectric constants, there are many ways to reference permittivity. So the first is what's called absolute permittivity. Absolute permittivity is a measure of permittivity of the material itself. So we've already been working with the permittivity constant of vacuum or air. It's the famous or infamous 8.85 times 10 to the minus 12. It's that constant that we've been using that gives us the Coulomb's constant, the 9 times 10 to the 9. That is the permittivity of free space or vacuum. Okay. Remember that always vacuum is going to be a reference because what exists in vacuum? Nothing. So that's the reference. Oh, your t-shirt is cool.
What is it for?
Excuse me?
You've
worn it before? I haven't seen it. It's faded.
Yeah, it's like
Yeah. You got it at H&M, right? Or not? Yes, you got it at H&M. Oh man, I mentioned about the metallic shirt.
No, I accepted it.
You what?
I accepted it.
That's a cool shirt. I also bought my daughter because the Metallica thing that they have the skull thing in most of the things from an artist called Bushhead. And I bought a pink shirt for my daughter. I have a picture of us like this, and it's a pink shirt with one of the drawings kind of like that, with the skull that says Metallica. And I bought a onesie for our baby, which is yellow and has a red skull and it says Metallica. So yeah, they don't know what they're wearing. No, Sarah doesn't know Metallica. So there you go. So going back to permittivity, materials have permittivity. So the reference is going to be vacuum. So the absolute permittivity is going to be the permittivity of the material. So the reference we usually have is vacuum, which is the 8.85. But any material has its own permittivity. Okay. Wood, foam, any sort of ceramic material. They're going to have permittivity. So absolute permittivity is going to be the permittivity of the material. Okay. It's called absolute because it's the value according to the material. Then there's what's called relative permittivity. And relative permittivity is the permittivity of the material, but with regards to vacuum. Okay, that's why it's called relative. So let's say that the permittivity of what material is this? Sort of plastic. Let's assume plastic. I'm just going to say a value right now for the example. Let's say that the permittivity of plastic, the absolute permittivity of plastic is 2 farads times meter, for example. That's the absolute permittivity of plastic. The relative permittivity would be to divide the permittivity of vacuum with regards to the absolute permittivity, and I'm going to get a certain constant, meaning the relative permittivity of plastic is, I don't know, 10 times, 20 times the permittivity of vacuum. That's why it's relative. Okay? It's with regards to vacuum. Usually the permittivity, the absolute permittivity is given by epsilon 0. Relative permittivity is epsilon with a little r on the bottom. And then the static permittivity is the permittivity of the material when it's exposed to a static electrical field. It's another reference of the permittivity of the material. It's a more specific reference of the permittivity. And lastly, the dielectric constant. Now, relative permittivity and dielectric constant are the same, or basically the same thing. Okay. Or in other words, the proportionality between relative and absolute permittivity is called the dielectric constant. So right now that I mentioned, I don't know, the permittivity of plastic is 10 times the permittivity of vacuum. that 10 would be the dielectric constant. It's how many times it is with regards to vacuum. Excuse me, go ahead.
Remember that in the last slide, it said that permittivity and dielectric constants are essentially the same for most purposes.
Mhm.
That is talking about just relative permittivity.
Uh-huh.
So absolute permittivity wouldn't.
No, that's a good observation. This one, we want to put it as a note, that's a good observation. So the observation in the previous slide is that we usually use permittivity and dielectric constant interchangeably. But really, if we're talking about relative permittivity and dielectric constant are the same. Absolute permittivity is going to be the value of for the material. The concept of both of them is interchangeable. Okay. And remember that all of this is in the PowerPoint presentations that are uploaded to what? And this is just a table, and we'd already mentioned this table. These are just a list of some materials or substances and the relative permittivity or dielectric constant. This would be the dielectric constant, another way of calling it. And so you find that certain materials are much larger. We mentioned this in some class. If you can get your hands on some barium titanate, then your capacitor is probably going to be very large. I'm not sure if that is even legal or safe. I was thinking more about safe, but yeah. So notice that some of the materials that have to, substances or components that we can find in the air are very close to 1. That means that they're very close to vacuum, very close to vacuum. But paper, for example, is 3.85 times the permittivity of vacuum. So actually, you can build a capacitor just with 2 metal plates and a piece of paper. Marble glass has a larger permittivity as well. It's 5 to 10 times depending on the material. The rubber is about 2 point, Teflon around 2 times. So those are just examples of some materials you can use. For your capacitor, you can use any sort of materials you can get your hands on that are insulated. Just the thing is that, for example, let's say you want to use Teflon or you want to use foam or something like that. Remember that one factor in the capacitor is the distance between the plaques. So what we really want is for the plaques to be really, really close together. We want something very, very thin in the middle. So if we have something that makes the Oreo or the sandwich very large, even if it has a very large dielectric constant, the distance, remember that it's inversely proportional. So we don't want a large sandwich because that distance is going to make the capacitance slow.
I have a question.
Yes.
For example, if we use, well, no, I will make that question later.
Later in private, it has to do with the capacitor. But okay. So this is just kind of to round out what we were talking about with regards to permittivity. By the way, for your calculations, because you have to demonstrate the calculations, this is what I would recommend, or for your design rather, this is what I would recommend. So go online, do a little bit of research about materials and dielectric constants. Try to identify maybe some materials that you can easily find. Usually in some capacitors, if you want to build a very simple capacitor, so paper or some sort of ceramic. So for example, that wax paper that is used for cooking, that's a good dielectric. Of things you can find or easily find. Then try to find the dielectric constant or permittivity of that material. What you're going to find is a reference. Okay. Yes.
I have a question.
Go ahead.
The relative permittivity is like the number of times 1029 something, or is it just
Oh,
like 8.6?
No, that's a good question, Eddie. No, it's this, so this value, the number that's 8 times 10, or 10 to the something is the permittivity of error. The 8.85 times 10 to the minus
So
12. The absolute permittivity is gonna be that value multiplied by this constant.
oh, okay.
Okay, so that would be so if we wanted the absolute permittivity of glass, it's 5 times 8.85 times 10 to the. So the absolute permittivity, that is gonna be usually times 10 to the minus 12. This value that we're seeing here, this is just this value as a constant. It has no multiple. So look online, find some values, and that is going to be a reference of the permittivity or the dielectric constant for your material. It's so you might find a range. If you find a range, like in this case, you're probably going to have to do an average or something like that. And the testing is going to give you the how approximate your result really is.
So Professor, does it come from the higher the relativity, the higher the permittivity, the higher the capacity?
It's directly proportional, correct? Okay, so what I want to do now is that I want to go back and do one more exercise. I want to go back and for us to do one more exercise that has to do with capacitance and voltage. And I want to do these exercises for them to be documented. We have the video, but also because in learning module number 3, we're going to be doing similar exercises, but with resistances. And the procedure is mostly the same. So I do want these for you to have. So this was problem number 4. Where we had this capacitor array and we wanted to find the equivalent capacitance. We had already done that exercise. But now we're connecting a 10-volt power supply to the array. And we want to find the voltage and the charge in each capacitor. Okay? And so we're going to do a procedure similar to the ones we did last class, but this is going to be a little bit more elaborate. So I need you guys to help me out with the calculation. Okay? Just so we have the calculations correct. So this procedure that I'm putting here, this is what we had already done. These are the steps we had already done to find the total capacitance or equivalent, which was 11.4 times 10 to the minus 6. We had already done that procedure. We don't need to do it. We don't need to do it again. Okay. If at some point you can't see, because I'm remind you, because I'm sitting here and I want to block this one. Okay. So. So with that, we did this procedure to find the total capacitance, and we go. Let's say that the procedure is going clockwise. Now what we're going to do is from the last value we had, we're going to go backwards to find each of the values of the capacitors of the voltages and charges for the rest of the circuit. Okay, so first off, we have a total capacitance that we found there. The first thing we're going to do is that we're going to find the total charge and the total voltage. So first off, we know that in this circuit, we have a 10-volt power supply that's connected to the circuit. So I'm going to draw it here. Yes, of course. We have a 10-volt power supply that's connected here to the circuit. We have a 10-volt power supply connected to the circuit, and I'm just going to draw it here on each of the circuits just so we don't forget it. Sure.
Do we need all the drinks?
Yes. Yes, because we want to know from where did we get each of the capacitances to be able to identify the particular individual voltages and charges. So we do kind of have to follow the sequence. Okay, I'm going to leave it here on the screen for a couple of minutes. Now, another thing, you guys, is that if you already remember that we already did this in class. So if you have the notes from when we did it, you can do it. You can continue it there. But I'm going to leave it here so you guys can write it down. Okay. Okay, we need to find, all right, then here in the bottom, find charges and voltages in each.
It's like beat of homework test.
Exactly, exactly. And it's exactly like the ones we did last class. Okay. So we have to find the charges and the voltages in each capacitor. I'm going to leave that there. I'm going to leave that there for a minute so you can, if you want to write it down, or you can start writing it down while we start working. We have to do that. We have to do the calculation. Okay, so the first. So again, we already did the procedure to find the total capacitance. Now we're going to go back to be able to find each of the individual voltages and charges. So first off, we already have the total capacitance. One thing we do know is that we have a total voltage. What is the total voltage of the circuit? 10 volts, correct. And so with those two values, I'm going to use, what color can I use? I'm going to use a darker brown here. Use a brown. We can find the charge. And how do we find the charge? The total charge. The total charge is going to be the capacitor, or the total capacitance, I'm sorry, times the total voltage, which would be 11.4 times 10 to the minus 6 farads multiplied by 10 volts. And so the total charge is going to be equal to, so please do that calculation. That's actually it's a very simple calculation. We could just say, give me a moment. Do that calculation, please. So if we multiply that by 10, a very simple way of finding that calculation is that this is going to be equal to 114 times 10 to the minus 6 farads. Okay.
The
Yes.
only thing we have to do is the second part of the last. Problem 4, right?
Uh-huh. The,
Part B of problem 4 the homework test. What we need to do.
yes. Uh-huh. Okay. So the only thing I did there, quick calculation, since it's multiplied by 10, then I just move this over here. Okay, so, yes,
Do I always have to put all the numbers like C1, 2, 3, 4, 5, like kind of when it's one left, like C1 through.
yes, you can use any nomenclature you want, just as long as it's clear and understandable. Yes, you could call it C1/6 if you want. Okay. Okay, so
Or you because we already have it from me.
we got it from the calculation. Okay, and remember that for each capacitor, we should have three things. It's capacitance, it's voltage, and it's charge. Okay, so right now we have the total capacitance. We already had it from the previous calculation. We have the total voltage, which is the battery that's connected, and we just calculated the total charge. Okay. Now, questions here before I jump to the next step. Okay, now, again, I'm trying to be systematic in the procedure so you guys can follow. This because we're going backward. This capacitor, which is the total capacitance, comes from the previous combination of two capacitors. Yes.
The charge will be in columns for why.
Oh, it's in columns. Good observation. It's not ferrets, it's columns. Correct. Thank you. Thank you, Andrea. Columns, correct. Thank you. So this total capacitance comes from the combination of these two capacitors over here, right? How were these two capacitors connected?
In parallel.
In parallel, okay? And so in parallel, what is the same and what changes?
I know, in parallel, we got voltage same and you distribute.
Correct. So the voltage is the same and the charges are distributed. So this means that I'm going to write them, I'm going to write it here because I want to leave some space for the, I'm going to erase this part here on the bottom because I need space for the calculations. So what Andrea said is correct. So the voltage is the same. So what voltage did we have previously?
10.
So the voltage in 1, 2, 3 is equal to the voltage in 4, 5, 4, 6, 5, and that is equal to the voltage we already have, and that is 10 volts. Okay. What is going to be different? The charge. So the charge in 1, 2, 3 is going to be equal to the capacitance of 1, 2, 3 times the voltage in 1, 2, 3. The capacitor of 1, 2, 3 we had already calculated. It's up here on top. It's 10, what is it? 0.05 times 10 to the minus 6 multiplied by 10 volts. And the, I'm going to write this down a little bit more to the left.
Professor, another question.
Yes, go ahead.
Why are we using 1, 2, 3 and 4, 6, 5 instead of like 1, 2, 3, 4, 5, and 6? Yes, like if we already have that.
Yes, so the total capacitance we already calculated, and that's the capacitance of 1, 2, 3, 4, 6, 5, and that is 11.4. And so the total voltage is 10 volts, and the charge is going to be the capacitance times the voltage. Okay. I think the question or the confusion is this, whatever has a T in it, is equal to 1, 2, 3, 4, 6, 5. Okay. So we don't need to calculate it again.
And why did we move a step back and chose the 1, 2, 3 and the 4, 5, 4, 6?
Oh, Because this capacity, remember that when we calculated the total capacitance, we were going from here to here to here to here to here to here, and we're reducing. So now we're unraveling and going backwards. So this capacitor here, how did I create this capacitor? I created it by combining these two. Right? So now we're going backwards. This capacitor, we're separating it into these two. So capacitor 1, 2, 3, 4, 6, 5 is comprised by the parallel combination of C1, 2, 3 and C4, 6, 5.
And we're gonna do that procedure for every step that we.
Correct. Yeah. So again, we went from this original one to the total capacitance. Now we're going backwards to find the voltages and the charges for each one. Okay, so yeah, it's so this is why I'm mentioning or stressing that the procedure is important. Okay, because we do the procedure, let's say clockwise, and then we're going to go counterclockwise to find the rest of the stuff. So going back here, I'm going to write it more to this side. Q 1, 2, 3 is equal to capacitor 1, 2, 3 multiplied by voltage 1, 2, 3. And capacitor charge 465 is equal to capacitance 465 multiplied by voltage 465. Please give me those two values and validate them. Up here, we have the values of the capacitance. Capacitance 1, 2, 3 is 10.05 times 10 to the minus 6, and capacitor 465 is 1.36 times 10 to the minus 6.
For 1, 2, 3, I got 1.005 times 10 to the minus.
We're going to leave it at 1.005 times 10 to the minus 4. Or 100.5 times 10 to the minus 6. And the charge of 465?
1.36 times 10 to the minus.
Correct, 1.36 times 10 to the minus what? Times to the minus 5, right? Yep. Because we're multiplying it by 10, so we just reduce one of the exponents. Okay. So we're still unraveling the circuits here. And so capacitor 465 comes out of what combination? But it's 4, 6, and 5, this combination that we have too. And how are these two connected?
In series.
In series. So what stays the same in series and what changes? Charge is the same, voltage changes, correct. So this means that charge 5 is equal to charge 4, 6. 5 is equal to charge 4, 6, and that's equal to charge 4, 6, 5, and that's equal to 1.36 times 10 to the minus 5 coulombs. And so the voltage is going to be different. So voltage 5 is going to be equal to Q5 divided by C5. Calculate that value, please. And voltage for 6 is going to be equal to Q46 divided by capacitor 46. Give me those values. And the sum of those should give me 10 volts. And remember the multipliers there when you're doing the calculations.
Oh, sure.
I got 9.06 and enter minus.
In which one?
In that, in the 5.
The 5, okay. To the -6. And the voltage of 4.6.
I started to do este procedimiento.
The Giselle procedure. Okay, let's do these calculations and validate. Enya already gave us a value, so please calculate so we can verify.
Yes.
Okay. 9.0, but Enya gave us a multiplier, so it was 9.06 times 10 to the -5.
No, -6.
Okay, so this one is 9.06. Okay, so, and voltage 4.6 then. Could you please calculate that one as well?
I don't understand where we got that.
Which one?
The church?
The 9.06.
We should be dividing the charge, which is 1.36 times 10 to the -5, divided by the capacitance. Divided by the capacitance number 5, and the capacitor number 5 is, we had it over here, is 1.5 microfarads. Please check that calculation. Please check that calculation again. 1.36 times 10 to the -5 divided by 1.5 times 10 to the -6.
Because I got, my calculator got, it gave me this. And it's e to the -12. I don't know how to convert that. I forgot the conversion. But I did that sometimes.
Yeah, but you're missing the 1.5.
9.06.
Also, but also with a multiplier?
No.
No, it should,
Without multiplier.
yes, just everybody check the calculations. In the voltages, we should be getting values more that more higher values. We should be getting low values. So it's 1.36 times 10 to the -5 divided by 1.5 times 10 to the -6 because it's microfarads. Okay. Yeah, so it should be the 9, but it should be without the multiplier, right? So it's 9.06 volts. Okay. Okay.
So when it comes up like this, it's just like how it is.
No, but you're still having an e to the -11. So
Maybe I have to put the parentheses.
okay, and voltage for 6 should be equal to Q for 6 divided by capacitance for 6. And actually, it should be the difference between 9.06 and 10 volts. So we should be getting 0.84 volts here.
Yeah, it was the parentheses.
There's the parentheses, yeah. I'm just doing the subtraction, but if you do the calculation, you should get this value as well.
Figure.
Okay. Now, capacitor 4,6, we don't need to bother anymore with capacitor 5 because we already found its value. But capacitor 4,6 is coming out of this combination over here on top. And what type of combination is that? Parallel. 4 and 6 is coming out of a parallel combination. What is the same in parallel and what changes? The voltage is the same, correct? So the voltage 4 is going to be equal to voltage 6, and it's going to be equal to voltage 4,6, which is 0.84 volts. And what is going to be different is the charge. So Q4 is going to be equal to capacitor 4 times voltage 4, and Q6 is going to be equal to capacitor 6 times voltage 6. So find those two values, please. Capacitors 4 and 6, remember that those are also microfarads. So it's capacitor 4 is 0.75 microfarads. It's times 10 to the minus 6. And capacitor 6 is 15 microfarads, which is 15 times 10 to the minus 6.
I got the charge of 6.3 times 10 to the -7.
Okay, the 4,
Uh-huh.
6. So let's verify these. 6.3 times 10 to the minus 7. Verify these, please. Yes. Yes, of course.
I got the same.
Same, perfect. Okay, let's do Q6 then.
I got 1.26 times 10 to the -5.
Yes, go ahead.
Why? No.
I love it when students are going to ask questions and then they answer themselves.
Because I thought like why wasn't this problem like the one we did in the rest of it, but I already found out that it is. This
one has much more capacitors than the other one. The other one.
Yes, it's because I was trying to make the same procedure.
Okay, now next up, we have capacitor 1, 2, 3 is coming out of the combination of capacitor 1, 2, and capacitor 3. How are those two connected? Capacitor 1, 2, 3 is coming out of the combination of capacitor 1, 2, and capacitor 3. How are those two? Parallel. So what stays the same? The voltage. So voltage 1, 2 is going to be equal to voltage 3, which is going to be equal to voltage 1, 2, 3. And we already had that one here on the bottom, which is the 10 volts. What's going to be different is the charge. So charge 1, 2 is going to be equal to capacitor 1, 2 multiplied by voltage 1, 2. and charge 3 is going to be equal to capacitor 3 times voltage 3. So find those two, please. Oh, well, actually, these are multiplied by 10, so it's actually easy. Capacitor,
It'll be just the same, but -1.
yeah, so this one is going to be 2.05 times 10 to the -5. And the other one, capacitor charge 3, what is the value of 3? It's going to be
8. Is that the
8 times 10 to the -5 coulombs. I'm just doing that because they're multiplied by 10. But verify them. We're just one more step to be done. Capacitor 1, 2 is coming out of the combination of capacitor 1 and 2. And how is that combination? Series. So that's the last one we need. In series, what stays the same? And what changes? Correct. So the charge of 1 is going to be the same as the charge in 2. And that is going to be the same as 1, 2. Which we had already found, which is 2.05 times 10 to the -5. And what's going to be different is the voltage. So voltage 1 is going to be equal to Q1 divided by C1. And voltage 2 is going to be equal to Q2 divided by C2. Yes. Go ahead, please. Go ahead.
With the charge of 0.6.
Okay, which one?
With charge 0.6.
Charge 6, this one?
Yes.
Okay.
If they are, when they're parallel, the charge is distributed, right?
Uh-huh.
So if we have charge 465, we should be able to subtract any of should be able to subtract any of the charges of 4 or 6 and get the result. I don't know if I can.
What should happen is that in the case of charges 4 and 6, which is this one here, the sum of these two should give us.
And it doesn't give me that.
And did you do the calculation or did you do it? No, it is because it's 1.26 times 10 to the -5, and it's 6.3 to the -7, and it's 1.36. So the 26, we're adding 26 plus 6 is going to be 32 plus the decimals, it's going to round out to 1.3. Okay, let's have those two last voltages, please. For the first one, 4.85, 5.85. Okay, please verify 5.85 volts. And so the difference should be 4.15 15.
And then for the second one, it's 4.1.
Mhm. Correct. Approximately. Okay. It's important to have a. Now, by the way, yes. So one way of doing it is to do the complete procedure and find the total capacitance and then go back. The other is that as you go along, you can also be calculating each of the values if you want while you're reducing them, as long as you have you're always going to be given at least the total voltage in these exercises. Okay, questions with this one? I'm going to leave it there so you guys want to write it down.
It's slow.
It is a slow Monday. It's going too slow for my.
No, pero tenemos
You have the workshop today?
It's fun, but it doesn't work.
Indian doesn't do anything in the workshop? What's happening there?
Where?
In
No, it's not true.
It's not true.
She just.
You supervise.
She just oversees us and she's like, no, you shouldn't be doing that. And
It's
then
because
she
they-
doesn't do anything.
They don't like to plan anything.
No,
They
and
just
then
like go
We,
straight to it.
we always
I don't
think
like
they're wrong because we're always correct.
What do you think about that, Enya? Is that statement accurate?
It is actually very accurate. It's very
No.
accurate. As
We
far
spent 2 hours, he just one, two.
because.
Really?
No.
Oh, no, that's not right.
One.
Ajá.
No manches. No, nos pulimos y en una clase. Ya
No.
está. Debería aprender a soldar.
Competitiveness in this group is tremendous.
No one wants to do anything, so.
Nah,
they
nah,
have
nah.
to do
No es
it.
cierto.
But we had
It's
like,
fake.
I was like, okay, we should do this, and I was telling her like, we should do this, and then this,
Yeah,
and then
she's
this,
like-
and then it was just like,
You're fired.
But she doesn't want, but she doesn't
How do
want.
you
she
say
doesn't, she doesn't get her hands on.
Well, yeah, well.
I feel
Depends,
just like
depends.
the person of.
So when Viviana said, how do you say soldar? So there's different, so if you're doing the large, it can be called welding. I think what you guys are doing is welding. But if you do it in a circuit board or something small, that's called soldering.
What?
Soldering. SODDERING. So I think what you guys are doing is welding, right? You're doing it with metal large.
It's fun.
Oh, you guys learned how to weld?
Yes.
By the way,
With that.
with the mask, well, it's important to have the mask, or not, it can be very dangerous. By the way, remember in your resumes, add basic welding. Those are.
It was supposed to be a line and I went.
You went like that.
No,
Actually, this is something that we receive feedback from companies and companies in the actually abroad. That's something that you guys have, all of the things you're doing in the manufacturing workshop. Those are really important for you guys as engineers and more as industrial engineers. Because actually companies tell us, we've got these engineers that have to design or optimize processes that have to do with welding, that have to do with, what else that you guys are doing? Casting, that have to do with cutting, that have to do with different things. But these are engineers that have never welded anything. So they're designing a process or optimizing a process of something that they have never done. So all these abilities that you're learning in the manufacturing workshop, put them in your resumes, because a lot of companies like that. And it helps close the gap between design and manufacturing. Okay, so it is important that you guys learn these things.
Like
For
basic.
example, if we
Basic
put-
casting, basic welding, yes.
If we put, oh. I
Well, don't put the O, the O is just.
If I put, for example, oh, I know. If I put, oh, I know basic soldering, but my soldering doesn't look very good.
Well, what you're gonna put in your resume, just put basic, the important thing here is basic, so basic soldering, casting, etc. And you can put in parentheses, manufacturing workshop class or something like that. When they do the interview, or they interview you, if they're gonna say, if you're applying for a welding certification job,
Uh-huh.
then, well, no. If they tell you, okay, Yesel, can you do this welding procedure or casting, you can say, no, well, I know the basic procedures and I've done it before. I'm not an expert, but I understand them. That's what you would be transmitting. That's why the word basic is important. If you just put welding or you just put casting, that means that you have more advanced knowledge of it. So the basic part is important, but do include it in your resume.
Professor,
Definitely.
in what we learned with Access with you last,
You
it's
could-
like basic.
You could, yeah, you could say basic, Microsoft Access and database design.
But you can
Because-
put advanced Excel.
Because advanced Excel. Because in the case of database design, you're not at the level as a computer science engineer, but you at least understand the concepts. And I would put that in your resume.
Or Microsoft Access.
Access.
I know how to navigate myself through Microsoft.
Puedes poner uso, you can just put